Hi everyone, I'm Noémie Legout from Uppsala University, and I will start by thanking the organizers for the opportunity to talk for this conference, Nearly Carbon Neutral Geometry and Topology conference. I'm going to talk today about joint work with Orsola Capovilla-Sell, Maëlys Limousineau, Amy Murphy, Yupan, and Lisa Traynor about obstructions to reversing Lagrangian surgery in Lagrangian fillings. So what do I mean by this? Assume you have a knot in S3 admitting an immersed filling in the ball before, then it is always possible to resolve the immersed point at the cost of creating genus, but it's actually not always possible, or it's a question to ask when you have a filling with a genus, does this genus comes from an immersed point that has been resolved? So in this talk, we're not going to stay in the smooth topology world, which is very flexible, because if you have a filling with one immersed point, you can always increase the number of immersed points, or you can always increase the number of increase the genus. So instead, we will be in a more rigid world where we consider a Lagrangian cobordism or Lagrangian fillings of Legendrian links. Moreover, we will add some extra conditions on the Lagrangian fillings in such a way that the genus and the number of immersed points of such a filling will satisfy, will be in a linear relationship. And if given one Legendrian, it admits a filling with some genus and number of immersed points, then all the other possible Lagrangian fillings with this extra condition will appear in this line, like in such a line. So resolving double points will be done by Lagrangian surgery in our case, and it means that it's always possible to go down in this line, as on the left picture. And the question is, can we go up in this line? Okay, so I'm going to recall what are the objects we consider. So we consider Legendrian links in the standard contact manifold R3. I recall that the red vector field is dz, and submanifold lambda is a Legendrian link if the contact form restricted to it vanishes. So on the right, I depicted the front projection first of a Legendrian knot, and then the Lagrangian projection of Legendrian knot. On this projection, this red arrow corresponds to is a rep chord, and on Lagrangian projection, the rep chords are intersection points. So now, if I take two Legendrian, lambda minus and lambda plus, what is an exact Lagrangian cobordism from lambda minus to lambda plus? Well, it's a submanifold sigma of R times R3 endowed with the two-form d exponential t alpha. So t is the coordinate on R. So this four manifold is what is called the symplectization of R3. And it's a symplectic manifold. So we take a submanifold sigma in it, such that there exists a real t positive, satisfying that sigma intersected with minus infinity minus t times R3 is a cylinder over lambda minus. So it's this negative end here. Then we assume that the positive end is the cylinder over lambda plus. And finally, the middle part, like sigma intersected with minus t times R3, must be compact. So this is topological conditions, and then we assume that there is a real valued smooth function defined on sigma, such that which is the primitive of the one form exponential t alpha restricted to sigma. So this means that sigma is an exact Lagrangian submanifold. And then some condition about this primitive that is constant on the cylindrical ends. So we denote it this way, and if lambda minus is the empty set, then it's a Lagrangian filling of lambda plus. That's what we call Lagrangian filling. And of course, so it can be, in this talk, it will be also sometimes immersed, so it means that we have transverse, so we assume it's non-degenerate, so we have a finite number of transverse double points. And they are all, because of those cylindrical ends, the double points are all in this compact part. Okay, so as I said before, resolving double point will be done by Lagrangian surgery, which has been introduced by Lalonde, Siporav, and Polterovich in higher dimension. So the goal is to resolve a double point of Lagrangian immersion, and the schematic picture of picture in dimension 2 is this one. If we have two Lagrangian or two Lagrangian disks intersecting in one point, the Lagrangian surgery consists in removing this intersection point and replacing it with those two possible models. So it's like two different Lagrangian surgeries. In the case where we have surfaces, so in our case, our Lagrangian will be of dimension 2. So it's the same thing that happens locally. So if we take a small sphere S3 around the double point, then it will intersect the Lagrangian on a Hopf-link. So I depicted here like the front projection of the Hopf-link and the Lagrangian projection. And then Lagrangian surgery is done by removing the ball before, whose boundary is this sphere S3. So we remove it and glue instead the Lagrangian handle, which is topologically a cylinder. Here, n equals 2. So this procedure will decrease the number of double points by 1 and increase the genus by 1. Here is a schematic picture of intersection of two Lagrangian planes. The green and red circle schematize the Hopf-link, or the two disks whose boundary is the Hopf-link, and we glue instead this gray cylinder. Okay, so as I said, we want extra condition on the Lagrangian fillings we consider, namely, we'll have restriction on the transverse double points. So if X is a double point of my Lagrangian sigma, I wanted to lift to a contractible Reb chord. I will recall what it means. This will ensure exactness of my Lagrangian after surgery. So if I start with a Lagrangian, with an exact Lagrangian, and I apply surgery, if it's done, if the surgery is done on X, which lifts to a contractible Reb chord, the Lagrangian after surgery will still be exact. And if it has Conley-Seidenberg 1, then if I start with Maslov 0 Lagrangian, I will end up with Maslov 0 Lagrangian. So what does it mean that it lifts to a contractible Reb chord? So if sigma is my Lagrangian in R times R3, I can consider its Legendrian lift, sigma tilde, which is a submanifold of the contactization of R times R3, which is the contact manifold with the one form du plus exponential T alpha. And in this contact manifold, the lift of sigma is this is given in coordinates like this, where F is the primitive of sigma. And it is actually Legendrian submanifold of R times R3 times R times R. So in this picture here below, I can, this is a schematization of a neighborhood of the Reb chord in the Legendrian lift. So if I have X, an immersed point, it lifts to a Reb chord in the Legendrian lift, which is schematized by this red line. And then it is contractible if one can apply Legendrian isotopy. If, like, under some Legendrian isotopy, it is possible to shrink the length of this chord such that it becomes length 0 without creating other chords of my Legendrian. So Casals, Murphy, and Plesas, they gave explicit parametrization of the Lagrangian handles in the surgery, the two Lagrangian handles of Lagrangian surgery, and they proved that these two parametrization, these two Lagrangian handles can be described in the Legendrian lift in the following way. So if you have length 0 chord, so which corresponds to action 0 intersection point in the Lagrangian projection, then you can remove this neighborhood and replace it by the cusp, this cusp sum or this cone sum. And when you do this, when you project back to R times R3, so you take the Lagrangian projection of this Legendrian, and you will get the two different Lagrangian surgeries. So in particular, we stay like, it means that it is possible if we start with a length 0 chord and replace it by this local picture or this local picture, then it means that we have performed, it's possible to perform a Lagrangian surgery in a way that the Lagrangian after surgery are still exact because they are Lagrangian projection of Legendrian, so it's always exact. So that's why we need this contractibility condition. And then this Conley-Zinder one is some compatibility condition for the Maslov to remain 0. So if we start with Maslov 0 Lagrangian sigma, it means that this Legendrian lift admits a Maslov potential. And I'm not going to say really much about this, but you can assign integer to sheets of the Legendrian. And for this Legendrian to also admit a Maslov potential, you need that this chord is Conley-Zinder 1, some compatibility condition. Okay, so this leads to the following definition: a vanishing index and contractible cobordism, so VIC, is a Maslov 0 exact immersed Lagrangian cobordism such that transverse double points have Conley-Zinder index 1 and lift to simultaneously contractible rep chords. Vanishing index is vanishing index in the sense of Legendrian contact homology index, which is Conley-Zinder -1. So as we saw before, this class of cobordism is stable under surgery. If I start with VIC cobordism and I apply Lagrangian surgery to one immerse point, the Lagrangian I get after that is still VIC cobordism. So it's still Maslov 0 and exact. And the question is, if we have a strictly positive genus VIC cobordism, can we reverse surgery? So can we increase, can we decrease the genus at the cost of increasing the number of double points, such that applying surgery will give back the first cobordism? And okay, the answer is no, and the motivating example is the following. So it's this Legendrian knot, which is topologically a 7-4. So it admits a genus 1 embedded VIC filling, an embedded Maslov 0 exact Lagrangian filling, obtained by performing pinch move on those two rep chords. And so we get this this knot, which after some random master move 2, you can see that it's a knot that we fill then with a disk. This gives this genus 1 embedded filling. And the question is, can this genus be replaced at, does the genus come from an immersed disk after applying surgery? And the answer will be no, as we will see. So that's so this example is the first example of a family of Legendrian. So if we have for G greater than 1 and P greater than 0, we show that there exists a Legendrian knot lambda GP, which admits a VIC filling of genus G with P double points, but not of genus G minus 1 with P plus 1 double points. And this theorem is actually a corollary of this theorem 2, which says that if I have a cobordism, an embedded Maslov zero exact Lagrangian cobordism from lambda minus to lambda plus, then the number of augmentation of lambda minus is always less or equal than the number of augmentation of lambda plus up to equivalence. It's a number of to equivalence. So for the remaining time, I will very quickly recall what is an augmentation and then construct or tell you what are the family of Legendre not satisfying this condition. So if you have a compact Legendrian, then you can associate to it Chekhanoff-Eliashberg DGA, which is an algebra, which is the tensor algebra of C lambda, where C lambda is the vector space generated by Rebbe-Corbs of lambda. The grading is given by Conley-Zeinder -1, and the differential is defined by a count of rigid pseudo-holomorphic disks with boundary on R times lambda. So R times lambda is in the symplectization of R3. So the boundary of A is given by a sum over all possible Rebbe-Corbs BI of the count of disk pseudomorphic disk like this, positively asymptotic to A and negatively asymptotic to BI. And then we write B1, etc., BM in this specific order. Okay, so by SFT compactness, it's possible to show that D square equals 0, and then the homology of this differential graded algebra is what is called the Legendrian compact homology of lambda. So I'm sorry, it's just extremely quick review. But then once we have this algebra, an augmentation of this Chekhanoff-Eliashberg algebra is a DGA map from A lambda to Z2. So it means that it sends to 0 all the generators which are not of degree 0. So it's a degree 0 map. It sends the unit like 1 to 1, the product to the product, and epsilon composed with the differential is 0. So if we know the differential associated to a knot by resolving some linear system of equation, we can check if there is an augmentation and compute all the different augmentation. So it's computable. So now let's prove this theorem by explicitly giving some examples of lambda GP. But first, we observe the following. So we will need the following. If lambda, so if my knot or if my link admits a VIC filling with P double points, then it's the same thing as having a VIC embedded cobordism from P disjoint copies of the Hopf link to lambda. So you just have to think that if you have immerse point, you take some small balls around, you pull it down, then you remove the balls, and you get Hopf links, and it gives you an embedded Lagrangian filling. So now, if we want to apply now, like theorem 2 is saying that if I have such an embedded Lagrangian cobordism, the number of augmentation up to equivalence of the bottom should always be smaller than the number of augmentation at the top. And we will use this to prove theorem 1. So first, let's, I recall very quickly the number of augmentation of the Hopf link. So if my immerse point is of Conley-Zeinder 1, it means that the Hopf link around it has this specific Maslov potential, meaning that those two chords B1 and B2 have degree 0, so they can be augmented. Then the differential looks like this, and the Hopf link admits 3 augmentation. Then by theorem 2, it means that if I have a cobordism, like embedded cobordism from p disjoint copies of the Hopf link to lambda, then the number of augmentation of lambda up to equivalence must be bigger than 3 at the power p. So now let's check again this first knot that we had, this 7,4 knot. It has, as we saw, it admits a genus 1 embedded VIC filling, but we can compute that it has only one augmentation. So it means that there is no VIC disk filling with one double point. Okay, otherwise it should have more than 3 augmentations, but it has just one. So this knot is the first of the family, lambda GP, so it's lambda 1, 1, 0. It admits a filling with genus 1 and 0 double point, but no filling of genus 0 with 1 double point. Then, okay, this was already known in the smooth world by Owens and Searle, where they proved they obstruct the existence of a disk filling with 1 double point for the 7,4. Now we construct more examples using this other knot, which is topologically 5,2. By pinching on this red vertical, on this red chord, it admits, one can see that it admits VIC filling with 1 double point. And one can compute that it has 3 augmentation. So then we perform some connect sum with the knot 7,4 that we had before. So the knot lambda GP will be a connect sum of G lambda 1, 0 with P lambda 5,2. So this is lambda 2, 2, for example. And by performing pinch moves, like on those red lines, it admits a VIC filling of genus G with P double point. But the genus comes from this, the 7,4 part, and double points come from the 5,2 part. And one can compute that it has 3 at the power P augmentation. So it cannot admit VIC filling of genus G minus 1 with P plus 1 double point. Otherwise, it should have more than 3 at the power P plus 1 augmentation, and it has not. Okay, so for this type of knots, the topological, like the smooth topology obstruction of Owen and Searle could maybe apply to obstruct the existence of these fillings in the smooth world, but as it has a big number of crossing, it is not so clear, because their obstruction work for some knots with a certain number of crossing, maybe 10 or a bit more, I don't remember. Okay, and finally we have some more examples, like with a very huge, possibly very huge number of crossing here. Those checkerboards, Legendrian links, which are constructed this way, they admit, again, by performing pinch move, they admit embedded Maslov zero exact Lagrangian filling of genus G. But one can prove that they don't admit any VIC filling of genus G minus 1 with 1 inverse point, because they have just 1 augmentation. I mean, it's possible to compute it. One way is to compute the number of graded normal rulings, which is a bit more easier to compute than augmentation in this case, but it gives just 1 augmentation. And finally, we can generalize this VIC fillings to the case where immerse points don't have only Conley-Zinder 1, but can have some other Conley-Zinder. For example, this lambda 948. So smoothly, it admits a disk filling with 1 immerse point, so also 2 immerse point. Then, by performing pinch move, it admits a Maslov zero immersed exact Lagrangian filling of genus 1 with 1 contractible immerse point of index -1. So the index -1 comes from the immerse filling of this Hopf link, and it gives an index -1 double point because of the mass of potential on this Hopf-Link coming from this cobordism, like induced by this cobordism. But then it has no, we can prove that it has no immerse mass of 0, exact Lagrangian disk filling with two contractible immerse points of index -1 and 0. So why is that? If it was the case, so if we had this filling with two immerse points, then again, we can take the two balls around those immerse points, pulling them down, and we would end up with an embedded cobordism from two Hopf-Links to lambda 948, but the Hopf-Link in the negative end, one of them is this one. So it has, because of the mass of potential, it has just one augmentation, trivial augmentation, and the other one, if it's Conley-Zinder, if it's index 0, so Conley-Zinder 1, it will have 3 augmentation. So the bottom, the negative end would have 3 augmentation, while this positive end, so this knot admits just one equivalence class of augmentation. So such an embedded cobordism cannot exist. So such an immersed cobordism with two contractible immerse point of index -1 and 0 cannot exist neither. While such a disk filling with, while a disk filling with two immerse points exists smoothly. So this gives like some, this obstruction exists just in the Lagrangian world. Okay, so I will stop here, and for those who are interested in the second part of the talk, I will give some ideas of proof of this theorem 2 that makes everything work. Thank you.